Hi, welcome to the analysis and design of a flyback. This is part 18, transformer design. This is probably the most asked questions regarding transformers, how to design them. I did cover them very briefly in one of the videos, uh, but I'm going to go a little bit in more details, a little bit more systematic, and actually give equations, and hopefully that they'll make sense. Uh, my end goal is to derive, or not derive the equation, but give the design procedure, and then show how we can wind them differently, and then perhaps test them, wind them and test them, and see how they affect the leakage inductance. Okay, since the leakage inductance has a big impact in your design, obviously we want to keep the leakage inductance as low as possible. So there's some techniques that you can do, and I also want to cover skin effect and proximities. That's not a well known subject, and I want to see if I can maybe uh, bring some light to those subjects. Okay, so when you design your flyback, most of the videos, or in fact all of the video, 1, 2, and 3, and so forth, what you're trying to do is you're trying to calculate the primary inductance that you need in order for your flyback to work. And here's a little bit more a general solution, or a general equation. Knowing, if you know what your duty cycle and your efficiency, and keep in mind the efficiency for a flyback can be anywhere from 0.7 to perhaps 8.5, 0.85. Okay, anywhere from 70% to 85%. Okay, and then of course this is your switching frequency. P out is your output power. Duty cycle, and we have a little constant here. Okay, so that should be straightforward. Okay, so once you have your inductance, the first thing that you need to do is you really need to see what core size. Okay, you do not want to pick a core that is too big, otherwise you're wasting capability. And of course you don't want to select a core that's too small, otherwise you won't be able to get your output power. So one of the methods that is used is you try to calculate what the area product would be. And the area product is basically the effective cross-section area of your core that you'll be using, and it's multiplied by the bobbing winding area. So you get this A sub B, A sub B, B. You get this A product area. Okay. And if you look in some of your data sheets, like say the Ferox cube, let me give you an example of where you would look at. Okay, here's an example. When you're looking at the data sheet of the cord that you're going to be using, they have the area, product area. Okay, so here it's listed as millimeters to the fourth. Okay, let me go back up. Okay, now the equation, that equation is from one of the TI application notes. You can look it up, but that's the equation. I give it here. PO is your output power. K is a constant, and this constant is for flybacks and forwards. The constant was just going to be 0.14, and this is your flux. Okay, in other words, this is the flux that you will be operating. Okay, and Ft is the frequency. Let me go ahead and do a SW, make it a little bit more intuitive. It's a switching frequency. Okay. Now, mind you that when you plug in your power, the flux density that you'll be using, and the frequency, the units will be in centimeters to the fourth. Okay. And if you notice, the data sheet that I'm using, they give the product area in millimeters to the fourth. So you have to make sure that you make the proper conversion. Basically, you want to make sure that you convert cm to the fourth to cm to millimeter to the fourth. Okay. Now, you may or may not have to do this, but the data sheet that I'm using, I do have to make the conversion. Okay. Once you get the cm squared, then you start looking in your data sheets. And what you're trying to do, oh, you know what? Let me backtrack a little bit. Let me explain this a little bit more. Okay, this can also be expressed as a delta B. Okay, or delta operate. Okay, and the reason I want to make that statement is you want to differentiate. And let me go ahead and put this as delta B, and you'll see why. I want to change the notation because there is a delta BSAT, which means that's the flux where it saturates. And typically, rule of thumb, it's 0.3. That's a very general, but it's plus or minus a couple. But you want to keep away from this. So, on the Pressman book, this is one of the books that I recommended. He suggests that your delta B somewhere around Teslas. Okay. So I want to be sure that you keep away from this, the 0.3, which is a saturation, and use delta B around 0.16. Now you can raise it. There's no problem with raising it, but you want to be sure that you don't exceed whatever your flux is. And of course you want a little bit of margin. Okay, so let me go ahead, go back I'll go for it. Once you do or calculate your AP, your product, then you can go ahead and start looking for cores. These are the cores. There's RMs, EPs, PQs, EFDs, and so forth. And I just happen to have this tabulated. And here I have the AP, and they're listed as millimeters to the fourth power. Okay. And once you want to make sure that whatever you calculate the AP that you calculate, select something that is a core that is bigger than your AP. So let's say if I have an AP of 100 millimeters to the fourth, then I could not use a RM4 because it's 81, but I could use a RM5, okay, and so forth. So this is where this chart is very useful. You can come down here and then select whatever you may have available. You can select the core that you need. Okay. Once you have the core, then you want to make sure that you select the proper material. This is very important. Right there. There are different types of materials, and they each have different characteristics or operating frequencies. Backtrack a little bit. You want to find, let me read this out loud. Find a suitable core material in terms of frequency and power losses. Okay. What does that mean? Okay. Here's a chart. If you notice, this is the operating frequency. Okay. And these are the charts that tell you the operating or the optimal operation of the core. So let's say this is 1 megahertz right there. Then I would not select a 3C. I would not get a 3C94 because it doesn't operate at that frequency, or at least it's not optimal. So in this case, I would come up here, and probably the closest would be this one, the 3F35, and so forth. So this is a nice little chart where you can select an optimal core material. In this example, I'm going to go ahead and use a 3F3. This is one that I've used where I work. And one of the things that you are looking for is you want to look for the B. In other words, you want to make sure what is the saturation. Basically, this is BSAT. Okay, and they'll give you two numbers. They'll give you a number of room temperature, which is 444 milliteslas, and a high temperature, 370. Now, mind you, the rule of thumb is that BSAT is going to be somewhere around 0.3 teslas, which is kind of close. Okay, so you can use this general equation, but if you want to make sure, always make sure that it's not lower than that. In this case, since it's bigger than that, then this this rule generally applies. Okay, so we know that 370 milliteslas or 0.37 teslas is a point that you want to avoid. Okay, you can go up, but don't exceed that, or have at least a little bit of margin. Okay, so now you have that. And let me backtrack a little bit. Okay, once you selected the core material and the core, and let's assume that I'm going to select this one. Then the next piece of information that I really need is this, the effective area, AE. AE is called the effective cross-sectional area. That you need that number, and that's in centimeters squared. And you need that piece of information because you need to calculate the number of turns that you need given the delta B that you will be using and the area or the effective area of the core that you'll be using. Okay, so once you have these two numbers, and this you get from your data sheet, okay, and this is of course a design. This is from your design parameters. Okay, then in this example it's a 3F3. The B set is, as I mentioned, is 0.37 teslas. So a general rule that you can use, you can either two rules. You can use half or your BSAT, or you can use the Pressman suggestion, which is 0.16. Okay, so anyway, you can use either the Pressman, which is 0.16 teslas, or you can use the 0.185, which is half of your BSAT. So that gives you enough margin to ensure that you won't saturate your transformer. Okay. Once you have that, then you need to find the wire size that can fit in one layer if possible. Basically, your bobbin or the winding area looks like this, and you want to, let me change colors. You want whatever N you calculate, let's say you calculate 10 turns for your primary, then you want to be sure, or your goal is, you want to see if you can select 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You want to see if you can fit 10 turns in one layer. Okay, so that's the next parameter. Okay, and once you select the wire size, meaning that you have to select the appropriate American wire gauge. Okay, basically you need to find out what is the diameter. Okay, and basically on this one is you measure the distance from here and divide it by the diameter, and that's the number of turns. So if you know the number of turns, you can do basically divide the length by the turns and you get the diameter. Then you can find out what the wire gauge that you need. Then once you do that, you verify the wire can carry the current. Okay, so from our derivations, we want to make sure that we also calculate the primary current. Make sure that we have it in RMS. And this is the formula. Okay, that goes in here. So basically I have this formula written twice here. And the formula is very important because then we can use this formula to make sure that we either calculate what the current is in the wire, or we can use a wire table. Okay, so basically we can look up, let's say if we use a American wire gauge of 20 of 20. Okay, what you can do is you can look it up in the table. In this case, I have 20 here, and 20 can carry up to 5.86. Okay, and if that current is less than your primary current, then you have to select a thicker wire, or you have to parallel the wires. Okay, if you don't have a wire table, you can use this formula. This is Precy's equation. This is the equation that you can use. If you know the diameter of the wire, you can plug that in. It's in meters, and when you plug it in, it gives you the fusing current of the wire. Okay, so basically you want to make sure that your fusing current is larger than your I primary current. Okay, I know that's a lot of information, so let's do an example. Hopefully it will make sense. Okay, so here's the design example that I'm going to be using. I'm going to use a input voltage of 24 volts, output of 12 volts, current of 2 amps, so that makes an output current of 24 watts, and I'm going to assume an efficiency of 0.8, 80%. Switching frequency is 100 kilohertz, and a duty cycle of 42%. Okay. So when I plug in the numbers, I end up with the primary inductance required of 17.8 microhenries. Straightforward. Okay. So now with the parameters, here's my cross area product equation. I now know what the output power is. Okay, and I know what the frequency is. Let me go ahead and write this as SW. Okay, which is 100 kilohertz. And the example that I'm using, I'm going to go ahead and use a Tesla or a B field of 0.185, which is right there. This is your delta B. This is the constant. Okay, so I end up with 0.042 centimeters to the fourth. Okay, and since my data sheets are displayed in millimeters to the fourth, I have to convert that, and all I do is multiply across these 1 centimeters equals 10 millimeters, and since there's 4 centimeters in the denominator, I need 4 of these in the numerator. So here's 1, 2, 3, 4, and then I need 10 of the millimeters up on top. Okay, so these centimeters cancel with the centimeters to the fourth, and basically this quantity is multiplied times 10, 100, 1,000, 10,000. Basically you move it 1, 2, 3. 3 spots. 2, 3, 4. Okay. Or actually 4 spots. So basically I have an AP of 420 millimeters to the fourth. Okay. So I need 420. Let's go back. And I happen to have these cores, and it's 420. I can't use this, but I can use a EDF 20 because it has a AP of 8 A1A, which is more than the, what was it, 420? 420. Okay, so since I selected that, then I need this number. That's the area, which is expressed in centimeters squared, and it's 0.290. Okay, so this is the one that I would use. Okay, and here's EDF 20. Okay, this is expressed in millimeters squared. Okay, the units change a little bit. Let me be a little consistent. Make sure that they match. 290. 290. Okay, that's the effective. Instead of using the 290, I'm going to go ahead and use what the actual data sheet. I believe that the program that I used the 290, so I'll go ahead and use this number. Okay. So now that I have that, I have an AP of, let me check that again, 0.310. Okay, here it is. Okay, so now that I know what my AE is, now I can use this equation to see the number of turns that I would require. Okay, I know what VN is, T on, and if it's T on, I can go ahead and express this a little bit different. I can use duty cycle divided by switching frequency, basically to equal T on. So there's another form of the equation. Okay, so now using these parameters, duty cycle of 0.42 switching frequency of 100 kilohertz, an AE of 0.310 centimeters squared, and I'm going to use a delta B of 0.185 Teslas. Okay. Then if I plug it into the numbers. Oh, and mind you, I'm converting this units to millimeters squared, because this is in terms of SI units, and SI units are in meters squared, not centimeters squared. Then I plug in the numbers, and here's my conversion, basically here. So I get a N of 17.57. So I'll go ahead and round that to 17 turns. Okay. And let me see. Okay. Okay. So now I know that the primary, I'm going to have 17 turns. Okay. So now what I need to do is, the bobbin looks something like this. The core actually fits. See if I can draw this properly. Generally looks something like this. Okay. So the wires, I'm going to go 1 layer, 2 layers, 3 layers, and so forth. So this length is what you need to extract from your data sheet. Okay. And on that case, I believe I have the bobbin here. You can either look that up on the drawing, or in this case, it says minimum winding length, which is 13.5 millimeters. Okay. In this case, I can change that to centimeters, so it's 1.35. Okay. So here's the length. Okay. And now what we need to do is also find what is they call it the build, or the height. Basically, how high can you build it up, or how many layers. Okay. So the main goal that you want to do, if possible, provided that you don't have one with a lot of turns, what you want to do is you want to fill 17 turns, or at least in this equation, you want to fill 17 turns in 1 layer. That way you can go ahead and put an insulator, and then you can build your secondaries after that. Okay. So that's the main goal. See if you can do it in 1 layer. And 1 layer, another reason to do it in 1 layer is because it reduces your proximity losses, and I'll try and cover that in the next video. But for now, let's just do it in 1 layer. And one thing that we can do is, if we know what the length is, and we know the number of conductors that we require, then if we divide that the number of turns or conductors by the length, we end up with the diameter of the wire needed to fit 17 turns. Okay. Once you have this measurement or this calculation, you can look in the table of magnet wire. Okay. In this case, I need that's centimeters. If I move this decimal here, then that becomes millimeters, so it's 0.79 millimeters. Okay, so we can look at the wire table, and this would be the number 18 would be the correct size of wire that you can use to fit in that one layer. Okay. Okay. So now we know that we can use a gauge of 20 to fit in 17 turns. Okay. Now once we have that, then the next is to check whether the wire can handle the current. Okay. Again, you can look in a table. In this case, the wire can handle up to 5.86 amps. Okay. So that's the current. Or you can use this equation. And when you use that equation, I get 5.85, which is fairly close. And you want to make sure that your current that you are driving through the primary does not exceed that value. Basically, you use this equation. Let me go ahead and copy that here. Let me go ahead and okay, so basically you want to make sure that the I is greater than your I primary RMS. Okay. Now, having those equations, which can be quite a bit of numbers or calculations that you have to crunch, it's more convenient if you can write or put those in a spreadsheet, an Excel spreadsheet, which is what I have done here. Okay. And let me go ahead and open this up a little bit on hide. Okay. So here, let me see if I can. Okay. So basically my yellows are inputs. Those are parameters that I input. Green are parameters that it calculates for me. Okay. And right here, these are my core sizes. And let me go ahead and zoom in a little bit. Okay. Here's my core sizes. This is my data regarding the cores. Okay. And if I type in my parameters of BSAT, core factor, power out, and so forth, I get my inductance here. Okay. And it calculates my AP in millimeters to the fourth or centimeters to the fourth. Okay. And then if the core size exceeds what I calculated, it turns green. So the ones in greens are cores that I can use. Okay. So that's what makes this table or this Excel nice, in that once you do that, it tells you, well, I can use all of these within that family. Since I have these available, okay, I'm going to go ahead and hide the rest, and these will be the ones that I'll be working with. Okay. And I believe it's right here. So let me hide. I'll hide that. And I'll hide this other ones. Okay. And let me zoom back in. Okay, so here, this is the cord that I'm going to be using to wind and do my various testing. And this core area is what I need. In that core area, I'll enter it here. And once I enter that, then I can come over here, and then it calculates what my primary turns will be. So in this case, it's going to be 17.57. Okay. And those equations are also calculate what the peak current is, the RMS current. And all I need to do here is type in the wire size number, and then look at this. When it turns green, it means that it fits. So in this case, if I use a American wire gauge of 34 to fill that one layer, I require 84 turns. Okay. So let me cut it to 24. So 24, if I use gauge 24, I will need 26 turns. And mind you, I need 17 turns. Okay. So I can keep on making this to what I had calculated, 20. And if you notice, it's 17.6. So this is a real neat way of selecting your wire size. Okay. And in addition, I have this where it calculates my current in the primary. My current in the primary is going to be 3.67. And my spreadsheet, I have where it calculates the current that the 20 gauge can handle. So since this is higher than my primary current going through the primary, then we know that wire is sized correctly, and we can use that. Okay, I'm going to go ahead and stop here, and in the next, I'll show a little bit more of the software, and then hopefully try to touch a little bit on skin effects and proximity losses as well. Thank you for watching.